Hello, Earth Science, and today we are starting Chapter 16, which is Wind, Waves, and Currents. In this chapter, we're going to talk about wind, we're going to talk about how it forms waves, and how these ultimately affect the landscape of the planet, create waves on the ocean, etc. Some really exciting stuff. So let's jump right in. So wind is an agent of change. Like rivers and glaciers, winds cause a lot of change to Earth's surface. They pick up and move sediment, they drive sediment against rocks, they drive it against other materials, and they cause weathering of these surfaces. Winds also contribute to the formation of ocean waves, and these ocean waves themselves erode entire shorelines. So wind is a very big agent of change on the planet. It has a big effect on Earth's surface. All right, so wind-blown rock materials. Wind erosion is most pronounced where we have lots of sand, silts, and clays that are lying loose and dry. Sand, silts, and clays that are wetter aren't picked up as easier. Larger particles aren't able to be carried by the wind. So optimal wind conditions for erosion include areas where there's large deserts, things like the Sahara in Africa or the Mojave in the southwestern United States. These conditions also exist on beaches or in semi-arid conditions where we're getting some times of the year where there's very little moisture, even though other times might have a lot. Dust storms. These are when strong, steady winds are lifting great amounts of silt and clay from the topsoil. During the 1930s, the United States had a very destructive dust storm that hit the Great Plains region of the United States. One of the reasons that this happened is the hardy natural grasses that were drought resistant in the region had been cleared for farmland. So once we got a drought and we no longer had these plants that were able to hold on to the soil, it was picked up and blown around. Dust can be blown so hard that it makes its way all up into the atmosphere. And once in the atmosphere, it can be transported great distances. Winds can carry dust over oceans. So normally, sand is carried much like sand in a river in short hops. This video here, like you can see the sand moving. It's not getting blown up very high. When it gets blown up way, way high, that's when it starts to go these longer distances. Usually it moves in these shorter saltatory jumps. All right, deflation. This is the removal of loose rock particles by wind. So this picture here is heavily deflated particles, and it becomes so much so that it becomes desert pavement. And desert pavement is when all the sands and clay that have been made by weathering are blown away, and all that's left is pebbles and boulders. These pebbles and boulders aren't heavy enough to be carried away by the wind, so they actually start to add some protection at this point in time and prevent deflation from occurring further. All right, blowouts. In semi-arid regions where we're getting some rain but not a lot, we can get these hollows called blowouts. And most of these blowouts are small and shallow, but some can be really, really large. These happen when we have an area of ground that's exposed without any plants or water holding down the soil. As the winds continue to move more and more silt and clay from the area, these blowouts get bigger, and eventually, if it reaches the water table, this wet ground stops the deflation. This wet ground is heavier, it's not as easy to pick up by the wind, and it will stop this blowout from forming. Abrasion. These windblown and clay particles have energy, and so even though a lot of times these silt and clay are too small to wear down rocks, things like sands that are a little bit bigger can have a little bit more effect. Silt and clays usually are more like polishing. They will make things smoother. Sand grains are able to be very abrasive. They can rip away big chunks of rock, and they can really scour these surfaces. And a lot of sands, these materials that have been worn down over and over and over again, turn into quartz sand grains, which are really, really small. And as we learned all the way back in chapter 5, quartz has very high Mohs hardness, making it a very good abrader. So it is going to really abrade these surfaces well. In this image here, we have a structure that has been abraded heavily. The softer rocks that were in this structure have already been abraded away, and the stuff that remains is a little bit harder. It has stood the test of time a little bit longer. All right, ventifacts. These are structures that we will find in areas with high winds. These blasts of desert sand grind boulders and small rocks into these ventifacts. These happen in areas where the wind is blowing, usually in a singular or in one or two directions most of the time. So these will show us which way the wind is blowing. The face that is having the wind blown against it here is the smooth face. And then the back side will be a little bit more rough and have dust accumulating over the back of it. So on this one up here, this first picture, this is the back of the ventifact. On this one, this is the front of the ventifact. If the wind is blowing in more than one direction, predominantly, it will wear down rocks on more than one face. All right, Loas. This is deposited sediment that has been deposited by the wind. So instead of removing sediment, this is sediment that's getting placed somewhere. So there are large areas in the United States, Europe, and China that are covered in these loas, and they are made of unlayered silt-sized particles that are generally yellowish in color. These deposits here are all loas. The particles are angular in shape, and they have been weathered by many different rocks and minerals. They can be as thick as 1 meter, or they can be up to 300 meters thick. So it depends on how much is being deposited and how long this rock has been deposited for. Sand dunes. These are hills of sand that have been deposited by winds. They form when sands pile up against shrubs, boulders, or any other obstruction. And to get a sand dune, you have to have very strong winds and a lot of loose sand. These are the kind of the materials that are made in the ingredient list for a sand dune. And sand dunes, like Loas, range in size from a few meters high to hundreds of meters high and thousands of meters long. They can be very large structures. So what are sand dunes made out of? Most sand dunes are made out of quartz sands. There are some exceptions, however. On the top picture here where it looks like snow, these are the dunes of the White Sands National Monument in New Mexico, and they are made out of the very soft mineral gypsum. And then the bottom sands here, these are when we have limestone or coral. These are calcite sands. They're a little more pink than your regular sand color. And dunes can also contain feldspars, micas, and magnetite. And all of these have a different color, have a different effect on the color of the sand dunes. How do they form? When we have wind blowing in a steadily direction, in one direction, we'll have this long, gentle slope up one side of the sand dune, and then a steeper slope on the backside here. These are just kind of almost the same shape as those ventifacts, but they're made out of individual particles, not an individual rock. The shape of this dune is going to be influenced by the size of the sand, the strength of the winds, and the amount of vegetation present to slow these wind things down. And we're actually going to jump into the different types of dunes next. So the different types of dunes. The first is bockhans, which form when strong, steady winds blow over a limited supply of sand, forming a crescent shape, and the ends of the barkhans are pointing downwind. This picture here on the right is barkhans. They're these little crescent shapes. The wind was probably blowing in this direction. And then the second type is transverse dunes, where sand is more abundant. They form long, continuous ridges that are forming at right angles to this wind. So wind's blowing in the same direction. These barkhans, however, are at right angles to it instead of little semicircles. All right, parabolic dunes. These are often form around blowouts. The open end faces upwind, and their long arms tend to become stabilized by vegetation. Vegetation will grow in that kind of deeper sand. Our transverse and parabolic dunes are very common on beaches, and our longitudinal, which are next, form in deserts more frequently. And longitudinal form when winds come from the same direction, and they get blown into long ridges that will run parallel to the wind direction. So instead of transverse, which are getting a shorter run, so they're getting blown in a 90-degree angle, these longitudinal or linear dunes are getting blown into long parallel lines. All right, so waves in the sea. An ocean wave is a rhythmic rise and fall of the water surface. And as they reach the shore, they erode and shape the shoreline. Water is a very good agent of erosion. We've talked about that in streams and glaciers and runoff. And generally, there are 3 different ways that ocean waves are formed. The first is undersea volcanoes can cause waves. The gravitational force of the moon pulls on the tides. But the everyday back and forth ebbing of the waves is most commonly formed by winds. Winds and waves. As we get gusty storms over the ocean or lake, it forms these ripples. As they get bigger, these winds get stronger. It blows the ripples longer and they grow larger. They become larger waves. The height of wind-formed waves depends on 3 factors. The first is the speed of the wind, the length of the time the wind blows, and the fetch. And the fetch is the length of open water over which the wind blows. The longer the fetch, the larger the wave. And the fetch is a very large piece of the wave anatomy. The shorter the fetch, the smaller the wave. So lakes, which have a shorter fetch, are going to have smaller waves than ocean waves. Normal and gale force winds, waves rarely get higher than 10 meters, which is 30 feet. During hurricanes, our winds can get even higher, and we can get even bigger waves during hurricanes. And strong winds that change direction often cause choppy seas, with waves that are of differing heights and directions, and they form those really foamy white caps as they're not being blown in one direction. All right, on calm days, the sea is likely to have smooth, steady waves called swells. This is what this picture is here. They are regularly spaced apart, they come at regular intervals, and they are caused by winds and by storms that are far off in the sea. So, the weather might be nice and sunny and calm on the beach, but out in the ocean, there's a lot of wind going on that are forming these waves. All right, the feature of waves. And these are for all waves, but we're going to talk about it specifically for water. The wave height is the difference between a wave's high point, which is the crest, and its low point, which is the trough. The wave length is the difference from one crest to the next. So stronger winds will produce waves with longer wavelengths, and waves produced during storms can have wavelengths of up to 150 meters. These waves are far apart from each other, very strong, very large. The period of a wave. The period of a wave is the time it takes one wave to pass a given point. In this image here on the right, this is a wavelength with a period of 1 second. For that wave to go all the way up and down, it takes it 1 second. Most ocean waves have a period ranging from 2 seconds to 10 seconds. And to find the speed of a wave, we can divide its wavelength by its period. So if we wanted to find in this example here, a tsunami that had a wavelength of 150 kilometers, that would be the wavelength goes on top. And a period of 12 minutes. We would take this, we would put it into our calculator, and we would get 12.5 kilometers per second would be our speed of this wave. All right, wave motion. Waterborne objects are not carried forward with a wave. Instead, they move in place in a circular motion. This is out in the ocean, not at the shore. In the shore, they kind of move back in. Furthermore, this circular motion happens below the water as well. As depth increases, this circle just gets smaller. It's the same circular motion. It is just smaller and smaller. As each water molecule moves, it passes its energy and this wave along from one water molecule to the next. All right, refraction. Instead of attacking a shoreline head-on, most waves come at it from kind of an angle. This is because as waves reach the shallow water, they swing around until they approach the shore head-on. This swinging or bending of a wave is called refraction. And this happens because the edge that's closest to the shore scrapes the bottom first and it slows down. The end that is deeper continues at a normal speed and catches up and overtakes it. And when it overtakes it, we get a phenomenon called breakers. And this is an image of a guy, he's kind of scooping it. It's played backwards of this ocean breakers here. As the wave scrapes the bottom of the ocean, the circular motion is distorted and the lower part slows down. The upper part keeps moving over it until there's no longer enough water to support it. At this point, it crests, falls over, and breaks into surf. The next crest will always be breaking in the same place, And this line is called a line of breakers. And this is what this guy is taking advantage of. He is making sure that he is scooping at that same place that that last wave crested at. All right, shoreline currents. So waves can approach the shore from any direction. When waves break or crash onto the shore at an angle, large amounts of water and sand are pushed onto the beach. The motion of water up the beach is called swash. And then most of the water runs back down the beach in a gentle current called backwash. As this process is repeated, the sand drifts down the beach in a zigzag pattern called beach drift, as it's pushed up and then kind of slowly taken back, pushed up, slowly taken back, pushed up, so on and so forth, as it moves from the zigzag pattern here of being pushed up and back and up and back and up and back. All right, so waves cause erosion. They strike rocks with thousands of kilograms of force. This removes large masses of sand and clay. As this water pushes into bedrock, it can create cracks. It can get into cracks. It will split bedrock apart further. Any sand or pebbles that is carried by the water will abrade the bedrock, creating more breaks in it. Seawater dissolves a lot more minerals than regular water, especially in rocks such as limestone. Some erosional features here we'll talk about are notches and sea cliffs. When waves cut away at a rock at the high tide line, it forms a notch. If the materials underneath this notch can no longer support the stuff on top of it, it will collapse, forming a sea cliff. In areas that have soft materials, this happens very quickly. So waves in like Massachusetts area, which has very soft rocks, will cut away very quickly. A lot of limestone in this area, as it once was an underground seabed. Underwater seabed. All right, shoreline features. In cliffs that are made of hard materials, a notch may deepen to form a sea cave, such as this one right here. And this is not a sea cave. Sea caves are like inside of rocks. Waves cutting through vertical cracks form what this is, and this is an arch here. If the roof of a sea arch falls in, what remains is a narrow stack of rock called a sea stack. And this is a sea stack here. There probably was a sea arch here at one point in time. Sea caves, arches, and sea stacks are common features on the west coast. All right, beaches. A beach is an area of the shore between high tide and low tide levels. The gentler the slope of the seafloor coming up to here, the wider the beach. Beaches can be sandy, pebbly, or rocky depending on the age of the beach. The makeup of the beach depends on both the available material, the slope of the shoreline, and the age of the beach. So first, where do these materials from beaches come from? Where's all the sand coming from? And most of the sand is things that were deposited by rivers that were then pushed onto the beach. They may also come from nearby beaches or bedrock in the area that's getting worn down. If the slope is steep, all the sands and clays will be washed out to the sea by backwash, leaving a very pebbly beach. So if you have these nice sandy beaches, it's probably a less steep slope coming up to here. And most of our beach sands are durable materials like quartz or feldspars. Sandbars. Along irregular shorelines, we get these longshore currents that are carrying sand and pebbles that are eroded from the headlands. Where this current passes in front of a bay or a cove, the mouth here, some of this gets carried inland to form a sand or pebbly beach. And this can form a sandbar. This is what happens when even more sand is carried and it's deposited across the mouth of a bay. The reason this is happening is because this water coming out from the bay is slowing down. It creates this kind of eddy that then it allows the accumulation of small particles like sand. There are different types of sandbars. If a sandbar is attached to the main continent at one end, it is called a spit. If this spit continues to grow and it crosses the entire bay, it's now a bay mouth bar. And if this spit has a curved end, it's called a hook. Sandbars do offer some nice protection. They kind of break the waves on the front there so that behind it is more quiet. These are usually harbors and great spots for crabbing and, getting clamming and all of these nice animals that like to live in these slower, more gentle areas. Another type of sand island is barrier islands. These are forming on coasts with straight shorelines. And they're not attached to the shore at all, where spits, hooks, those baymouth bars were all attached to the shore. Barrier islands are not. They're very common on the East Coast, and they are not permanent features. They change as the ocean currents change. They change after big storms, they change seasonally. There is people who make money just knowing where these sandbars are and guiding ships around them, being like riverboat captains. So they're very cool features. All right, irregular shorelines. So irregular shorelines are formed when coastal areas were flooded by the sea. This occurs in two ways. A, the land sank, or B, the ocean rose. So the sea did rise at the end of our last ice age that we talked about last chapter. These drowned valleys became bays, and the mountains became the new headlands. So many hills became islands, and this is a very common occurrence on the East Coast. The beaches there aren't really set up very well yet because they're not very long. They're not very old. All right, fjords. During the last ice age, once again, glaciers in Norway, Alaska, and other near polar regions were reaching all the way down to the oceans. They formed glacial valleys that were well below the present day sea level. When these glaciers retreated, they left long, deep, steep-sided bays called fjords. And these guys are saltwater. They're mixing with that saltwater. The tributary valleys are hanging valleys, usually with large waterfalls that are falling right down into the ocean. And they look pretty. There's a cruise ship in this one here. This one's in Norway. It's very, very exciting, very cool geography. All right, regular shorelines. So the shorelines of the west coast of North and South America are comparatively regular compared to the irregular ones on the east coast. They don't have very many deep indented inlets. They don't have drowned valleys. They're mostly regular as they're on the boundary line between two sets of plates. There's usually long mountains parallel to the ocean because these plates have undergone some subduction, made these really, really long mountain ranges. They have these really, really nice beaches. Good place to vacation. I hope that you learned a whole bunch about wind, about waves, about currents, about beaches. I hope this taught you a whole bunch about this topic. I hope you enjoyed it, and I'll see you in the next one. Thank you for watching.